Good evening, everyone. I'm Srinivas, and welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Dr. Ruihao Lee. He will be speaking on Oneiros, KV cache optimization through parameter remapping for multi-tenant LLM serving. Dr. Ruihao Lee is a research scientist at Meta AI and Systems Core Design Group. He received his PhD from the University of Texas at Austin, advised by Dr. Lizzie K. John and Dr. Neeraja J. Yadwarkar. His research interests include power planning and management of data centers and efficient memory allocation and management for CPU GPU systems and workload characterization. Over to you, sir.
Thanks for the introduction, and let me share my screen. Okay, sorry. Just 1 second. Yes, is my slide showing correctly?
Yes, sir.
Okay, let's start. So I'm very happy to present our recent work on Oneiros KV cache optimization through parameter remapping for multi-tenant LLM serving. So this work was published at SOCC in 2025. So mostly it was just accepted about 2 or 3 months ago. So I'm very happy to present this to this seminar. Yes. So as the title suggests, so why we are doing KV cache optimization for LLM inference serving? Because KV cache is very important and it could affect LLM performance significantly. So first I want to talk a little bit about why we study the LLM performance. Why just we need dedicated systems for LLM inference serving, not like just reuse those inference serving systems for CNNs, for other traditional ML systems. The reason is that there are additional concepts in LLM inference serving systems, which is called KV cache. And there is not only to store those model parameters and those activations. The KV cache is used to store those intermediate results, and it's specifically to large language model inference serving. That's why there are tons of work to study the LLM inference serving systems, because it's different from traditional ML serving systems. And why KV cache is important? Because KV cache impacts its performance. And here we have a figure to show this. The x-axis shows the request rate, which means usually like the RPS, how many requests coming in the system, or how many requests you are serving in the system. As the request serving rate increase, your available KV cache may have been reduced, or you have consumed a lot of KV cache when you kind of like allocated it like in your system. And when running out of KV cache, there is a problem. Your latency will increase significantly. As you show here, when you're running out of KV cache, you might result in like more than 2x like serving latency. The reason is that you have KV cache to store those intermediate results. But if you are running out of your KV cache, you have to recompute all these intermediate results, which results in significantly more computations and results in much higher latency. Like before I go to all the technical details, I also want to give a like brief introduction of LLM inference serving systems for introduction for those people who are not working in these areas. So for LLM inference serving sequence or LLM serving request or whatever, so there is always usually like the input and output. For example, here you are using ChatGPT or using Gemini. You ask the questions, say, what's your name? That's considered as input tokens. And for LLM inference serving, as long as you got the input tokens and you load your model parameters, then you start serving. And the first step of the inference serving is the prefill phase. As you show on the right side, it will go through those many layers, and then for those prefill phase. This figure is a little bit complicated. Let me try to simplify this. For those middle point, we can look at the abstract level of all those layers, which is called attention blocks. And there are many of those attention blocks of one model. For example, for the Llama model, there are like depends on the parameter size, there might be like 24, 32, or 48. That's kind of attention blocks. So for the case of Llama, all the attention blocks, the structure is identical. It's just the parameter, the real number of the parameters of these layers are different. For some emerging like LLM models, there might be the attention blocks might have different sizes. They are not necessary to be identical, but I want to just show an abstraction of all it looks like. It just goes through many of the attention blocks. It may be same or maybe not, and we'll do this like model prior to do this model computations. After the prefill phase, it go to the decode phase. So we can think of that the prefill phase is mostly about understanding the question to understand, oh, I got the input tokens are what's your name? And the decode phase is really about generating the answers of these questions. The interesting thing is that for LLMs, the decode phase will go through exactly the same layers of the prefill phase. Will share the same parameters of the prefill phase and go through this again. The difference is that the decode phase will execute it multiple times because it's generating tokens like one by one. For example, here the output like result may be like I'm Oneiros, and it's generating 3 words. So that means we'll go through this decode phase 3 times. So in conclusion of the entire LLM inference serving system, like the prefill phase will understand the question and will process only once. And decode phase will generate output like one word by word. It will execute multiple times, depending on your output total length. With hundreds of words, it will execute hundreds of times. So KV cache is a concept mostly helpful for the decode phase. Let's go through this again. Like the input is I am, what's your name? And it will generate I am Oneiros, 3 total words. So think about that for the LLM inference serving systems. When for decode phase, every time you generate a new word, you need the information of all the previous informations. So for example, you generate Oneiros, you need a context say I already generated I am. That's why you need those token values like key token for take token 1, key token 2, and value token 1, value token 2. So KV cache means like when you are generating Oneiros, all these previous tokens, the key values, the key and v values are already buffered in GPU memory. So you do not need to recompute the key token 1, key token 2 again when you are generating Oneiros. That's why the KV cache could help reduce the computation time significantly, and very importantly, LLM inference serving. Think of that when you're generating a new word. If using KV cache, it's mostly like a GenV operation, a matrix to vector operation. But if you're not using KV cache, it's mostly like the matrix to matrix multiplication, which will like increase the number of computations to the next level, like computation complexity. And we can also know that because you need the KV cache, you need to buffer the key and v values of all the previous generated tokens. That means the size could grow like linearly as the sequence length increases, and may also grow as the number of batch size increase. After we go through like the most basics about like how the LLM inference serving system look like and how we do this, how the KV cache functions in LLM inference serving systems, I want to talk a little bit also more about the background session about like how existing state-of-art systems deploy LLM inference serving engine. So most of it will deploy in a CPU-GPU heterogeneous system because GPUs are widely used to speed up those processings. But before really we kick off the competition on GPUs, we first need to load parameters. Load parameters first from disk to CPUs, but I didn't show it here. I just first show like load parameters from load parameters from CPU DRAM to GPU HBM. Then the first step, you load parameters. And then once you deploy the engine, like deploying the inference serving system, you have already loaded the parameters. You can serve the input tokens. And also input tokens are coming from through network or through other interfaces, and then loaded to GPU memory. And also it then starts the prefill phase first by executing the LLM kernels on the GPU side. After the prefill phase, it will start generating KV cache, and the KV cache will interact with the LLM kernels like between the decode phase. And after finish the entire decode phase, it will generate all the output tokens. The KV cache need to interact with the LM kernels because you are generating word by word. So you are upping the KV cache word by word. That's why there are those interactions. And after you finish all these things, you will just finally store back the output tokens to the CPU memory. That's the whole process of a typical LM inference serving systems. However, we found that like the KV cache and GPU computation kernels are interacting like frequently, which will make fully utilize of current state-of-the-art GPUs like terabytes per second, the GPU HBM bandwidth. However, we do not find there is enough interaction between CPU DRAM and HBM memory during the entire serving phase. We only find that like we load parameters only at once because for all the input token is coming, we don't need to load the parameters again. The input tokens loading and output token storing, it might like being active multiple times. But these are like only megabytes level. It didn't fully utilize of the CPU GPU bandwidth, especially for existing systems, it may reach to like 450 gigabytes per second. That gives some opportunities for optimization. We could use CPU memory as the extension of GPU memory to store parameters or KV cache. That way, we could support a longer sequence or support a larger byte size. And we could move the KV cache from CPU to GPU memory in between, and also like load and store the parameters from CPU and GPU memory in between to kind of like increase the effective capacity of GPU memory. So this is feasible with emerging hardware like CPU, GPU technology support. This figure shows the trend of the CPU memory capacity increasing and the CPU, GPU memory bandwidth increasing. We can see that I use an example of NVIDIA GPUs. So from P100 to GH200, the GPU memory capacity did not like increase significantly or like have a like very surprise increase in recent years, but the CPU GPU memory bandwidth has recently increased in GH200 significantly because of the NVIDIA recently introduced those like NVLink technologies like chip-to-chip connections. So for H100, it only supports like for directional like 128 gigabytes per second GPU CPU DRAM to GPU bandwidth. But for GH200, it supports 900 gigabytes per second CPU GPU bandwidth. For each direction, it's 450 gigabytes per second. Say you're reading memory from CPU DRAM, the reading bandwidth could reach to 450 gigabytes per second, which is about 7x more than its previous generation, just H100 only. And we're talking about offloading part of or swapping part of the KV cache or model parameters from CPU to GPU memory. This is only feasible with enough CPU GPU bandwidth support. The right figure kind of like give a model of this. It's a little bit complicated. I would like to spend more time to explain this. So the x-axis shows the serving batch size, and the y-axis shows the time between token latency, which you can like consider it's just as a latency. And as you can see that the batch size, as batch size increase, your server latency is also increasing as the batch size increase. The case is that when you want to offload part of the parameters to CPU memory, we could also think of another scenario. We could use CPU as the engine to do the computation instead of like a secondary storage for the GPU, right? But if the CPU, so there are two scenarios. One scenario is CPU GPU memory bandwidth is limited. For example, H100. When you are loading the 30% of, you are kind of like swapping 30% of the model parameters. The time for loading these parameters is already like more than 100 milliseconds, which is about like when you're doing it's also worse if the batch size is low. It's also even worse. You just doing the computation on the CPU side. That's on the left side of the figure. You don't need for this like this KV cache or parameter swapping. And for the case like you want to swapping like all of the parameters, you need to reach a very high batch size, which is not that kind of relation in most like online serving systems. But when you are doing you are using GH200, like your CPU GPU data transfer time is significantly lower than the computation time on the CPU side. That means it's not worth to use CPU for the computation. You just load the data back to CPU and move it back. This is more effective solution. That's why it's something like KV cache swapping or parameter swapping is something like feasible in these recent hardwares. So we have talked about like swapping parameters or swapping KV cache for large language model inference serving systems. It's feasible in these emerging hardware systems. But right now, we also talk about it's necessary or we must have it. So this is something like show from another paper like for dynamic LLM, which the HPC 2025 Best Paper Award. They have proved that in a production system, your load variance, your LLM inference serving load varies across time significantly. That is more than 4x or 5x. That means at some time point, your entire system is underutilization, but you also need to handle the case when like the full load, the peak load arrives. And this is very challenging for capacity planning. For example, a conservative plan can leave resource idle for most of the time. For example, you want to deploy 100 GPUs for your inference serving system. It may be underutilized for those hours that are not like peak hours, but it may be running out of KV cache for those peak hours. And Oneiros is a backup plan for this time period when it's really reaching the peak. And because you don't know your exact coming request rate, you don't know your exact like the batch size, your exact sequence length. So you need to have a backup plan. When the peak time reaches, you could use Oneiros as a backup plan to use CPU memory extension for GPU memory, which is necessary because running out of KV cache, your server latency may increase like significantly and result in some service level objects like you didn't meet the service level objects in SLOs. Okay, now finally we are talking about our design of Oneiros.
Hello.
There,
Uh,
yes.
Sir, there is a question. Does
Okay.
compute offload lead to any synchronization overhead?
Yes, that's a very good question. Either computation offload or parameter offload, there is an overhead. Like you mean the overhead of the synchronization process or
Yeah, hi. That was my question.
okay.
Earlier you mentioned that you're going to offload few of the computations to, I mean, the KV cache also you are going to share with the CPU, right? So like, how are you, like, is the prefill, does it belong to the same request? And if they belong to to different requests, then won't there be any synchronization required between the CPU and GPU memory?
I see, I think I got the point. So the question is mostly about if you want to CPU offload the computation, how would we handle the KV cache, right?
Yes.
Okay, so the case is like the KV cache, it belongs to per request. It's per request only. It doesn't need to share your KV cache with another request. So we are offloading the CPU computation. Mostly means the case, the entire decode phase is processed on the CPU side. So you don't need to bring the CPU, load the KV cache to the GPU memory. That's why your latency may be very high when your batch size increase. Maybe let me go back even earlier for this figure, right? So as even you are doing like a jump weight operation, as long as you are increasing the batch size, your jump weight operation is also pretty heavy operation for CPUs. That's why you see this. As talking about the synchronization overhead, I would not expect too much. So like the computation itself is taking more time to the really synchronization overhead if you want to offload computation to CPUs. And I believe there are some recent works talking about offloading computation to CPUs, which is, I think it will show up in HPC this year. There will be some papers talking about this. And there are some ML6 papers in 2025 also talking about those like offloading computation to CPUs. Yes. Does this answer your question?
Yeah, thank you.
All right, thanks. Okay, let's now talk about the design of Oneiros. So first we want to decide whether we want to do KV cache swapping or parameter swapping, because those something like both two are options for LM inference serving systems. We want to use CPU memory as the expansion of the GPU memory. First, let's talk about KV cache swapping. So KV cache swapping, we do not swap the entire KV cache. We only swap like a few layers of a KV cache to store them in CPU DRAM. The reason is that, like, as we have mentioned before, like the attention blocks, there are many attention blocks. There are maybe 32, 24, those attention blocks. And we only and the KV cache is also a per layer concept. So each layer has the matrix of key values and V values. So it's possible to only offload or swap a few layers of KV cache to CPU memory. And to expand the effective KV cache, the reason is that we offload the KV cache to CPU memory when we finish execute the current layer, and when we are only loading these layers of KV cache to GPU memory, we are really executing this layer because we are executing this like layer by layer. So this is like doing this in a double buffer technique or something. This makes this possible. Mostly like when you are doing the computation, you are doing the data transfer in parallel and to pipeline the entire process. As long as you decide the current size of how much to offload, it will almost achieve the perfect pipeline. So the CPU GPU data transfer will not become the bottleneck. And the prior work already proved that it could help reduce latency by up to 2x if you're doing the KV cache swapping. However, there is also challenges or limitations of this KV cache swapping, because every time you generate a new token, you need to update the KV cache. That means you need to have a backup of the KV cache to CPU memory all the time. Every time in your GPU you generate a new token, you need to back up to the CPU memory. That's the dual directional data transfer will incurs like significant frequent synchronization. It may introduce additional overhead for this KV cache swapping. So our proposed methodology is about doing parameter swapping instead of KV cache swapping. The reason is that parameters are constant numbers. It never change or update during the inference serving process. And we only need to like swap, similar as KV cache swapping, also swap partial layers of the parameters to CPU memory. And when we are not executing the layers, we do not need this. We only need to load from CPU memory to GPU memory when we are really executing the layer. And we also have a detailed controlled pipeline of this to make sure we are overlapping the GPU computation and CPU loading time effectively. And this will come with negligible synchronization overhead because we do not need to stop the GPU pipeline. For this, we need to back up the data to CPU memory, because every time we need to add barriers here to make sure like data is consistent across CPU memory and GPU memory. Right now, we don't need that. We only need to wait until the data loading is finished, then start the computation. It's far way easier than like this dual directional synchronization.
Hello. So,
Yeah.
sir, what does this remapping mean? I could not follow.
Yes, remapping is, so we use swapping is like for the dual directional. Remapping is only single directional. We only load parameter from CPU to GPU.
Okay,
So basically, like parameter have many layers, right? Say we have 32 layers.
right.
Currently, we are executing layer 1. So technically, we only need layer 1 on GPU memory.
Okay,
We are
understood.
executing layer 2, only need layer 2. But when we finish up executing layer 1, we could disable this part of this memory and use this memory for KV cache to expand the size of the KV cache. And when we are executing layer 1 again, we load the parameter again.
So, sir, when you are excluding it, where are these parameters stored? Do we need to store it somewhere or we calculate it again?
The parameters are constant numbers. The first we load from disk to CPU memory. It's already constant. It's already existing CPU memory, like for the entire process. As long as we need something, we move to GPU memory. But existing LLM inference serving system to load all the parameters one shot ahead of time.
Okay, clear. Thank you, sir. Understood.
So we'll break down this in a finite quantity in a layer-wise operation instead of like for the entire model as a granularity.
Okay.
Okay. Yes, so parameter remapping is still a challenging problem, especially for nowadays multi-agent or multi-tenant systems, because right now the model does not need to be like very big models. And the GH200 is a super computing chip. It could host multiple models together on an entire node. That's why they are introducing challenges for this multi-tenant systems, and there is no study about that. And there are four key challenges we figure out and we want to address in the Oneiros. The first is when to trigger parameter remapping. The second one is for the multi-system, which model we want to remap. And third one is how many layers to remap, because we'll break down the granularity to per model to per layer, and also which layers to target or for those remapping. And then we developed the system Oneiros, which about dynamically remap parameter memory to elastically resize the KV cache in multi-tenant LLM inference. So Oneiros could be integrated into existing like LLM inference serving system easily. So we actually developed Oneiros and we kind of integrate Oneiros into vLLM, which is one of the most popular inference serving engine nowadays. So Oneiros has three major components. One is metadata store. The other is remapping controller to make the decisions, and also async transfer engine to control the CPU-GPU data transfer. And for the entire process, so Oneiros could utilize the existing like inference serving system scheduling policies. Or for example, here we use the existing vLLM scheduling policies. Something I want to emphasize is that Oneiros does not could be compatible with all these existing schedulers, and the scheduler itself is not our major part, but our part is like mostly a engine to help support this like CPU-GPU data transfer. So the scheduler decides which model to serve and will update the metadata store. And after the scheduler decides which model to serve, the memory allocator will allocate the GPU memory for parameters or for KV cache usage. And after that, both will update like the which model and the KV cache status of the GPUs to the metadata store. And based on the metadata store, the remapping controller will make the decision like whether to remap parameters or not. If we have enough memory, we don't need to remap. We just run it at what it is. And if not, we are starting the asynchronous transfer engine, which is about like doing this parameter remapping dynamically. And this is the next step of Oneiros. And the last step is GPU will activate the LLM inference serving task and send everything to the GPU side. This is the overview of Oneiros about its component and how the execution flow. And as you can see that like the most important key thing is about the remapping controller for Oneiros. And next slide, I will go to the more details of our remapping controller and how our remapping controller would address the four key challenge questions I have mentioned before. So first is about when to remap. We only remap when KV cache runs out. I will use the example here, like we have three models deployed in the GH200 in the Superchip, Model A, Model B, and Model C. And currently, Model A is the active model. We are executing Model A, and Model B and Model C are currently like idle models. Like we either need input from Model A, or there's no input coming from Model B or Model C. We only remap when we start remapping when we run out of KV cache. Because we have enough KV cache, we just run the exact same thing as vLLM. We don't need to use CPU memory as a extension for GPU memory, because all these pipelines, even a perfect pipeline, may come with performance overhead. We need to take care of this very carefully. And then the case is that when KV cache runs out, we start to enable the Oneiros. And when they start to enable Oneiros, we want to expand the KV cache size, we want to having more GPU memory allocated for KV cache. They want to kick out some of the parameter memory space. Then the question comes out like which model we want to remap. And the decision of which model to remap is very intuitive for this case, because right now we are assuming model A is active, then definitely want to prioritize these inactive models because it has a longer waiting time. to make sure if the inactive model executes this layer, we will have enough time to load the model, load the parameters from CPU memory to GPU memory. Then we are prioritize those inactive models. And this is decided by the scheduler. If the scheduler didn't decide, say, which model B or model C, which has higher priority, we're just doing this in a round robin fashion to give a fairness of all different models. Because for our online system, we do not exactly know which request from which model comes first. The round robin is not perfect, but it's the most effective and fairness for all the models. And the next thing, more important, is how many layers to remap. Definitely, we don't want to remap the entire model B or model C, the inactive model. We want to do this like layer by layer, or like in an on-demand fashion. Say we are running out of KV cache, we remap one layer of the models. We are running out of again, then we remap one layer again. We do not like remap the entire models because if we don't want to CPU-GPU data transfer becomes the new bottleneck. And we are calculating this like very carefully because like we have a runtime profiler to capture like what exactly the execution time of the decode layers. They are running this perfect pipeline. We are knowing the exact computation time by profiling, and because the CPU-GPU bandwidth is like a constant number, we can calculate this offline. And the size of the parameters, which is also a plus for remapping parameters, because the size of parameters is also known ahead of time, so we can calculate this like very easily. As long as we know the time of computation, we can know like what's the maximum number of layers we can do remapping or transfer between CPU, GPU to make the transfer part not becoming the new bottleneck. And the next part is like which layers to target. This is a little bit complex, and we have explained this quite more, have dedicated session in the paper to talking about like which layer to target. And here I want to go through like very high level of it, but won't go to all the details of like how we do this mathematical proof of why we choose these layers. So like simplify this, we use a uniform interval layer selection strategy, which we choose evenly spaced layers for this parameter remapping. For example, here, if we want to remap the parameters of model C, we pick layer 1 and layer 5 if we want to like to remap 2 layers. Something like thing is like why we don't do like layer 1 and layer 8 and we are doing layer 1 and layer 5, because we want to pair layer 1 and layer 8. I draw this in a circle because I want to emphasize for LLM, it's something like kind of like a circular execution for the decode phase, because decode phase executing multiple times. So doing these rings like multiple times, generating word by word. So think of that. You are doing computation of layer 1, definitely have enough time to load the parameter of layer 8 to GPU memory. You have 7 or 8 layers like in between. But you are finishing up like layer 8. You need to execute layer 1 again when you're generating next token. But for this one, you don't have enough time. That's when we are doing this like uniform layer selection strategy. And we have a lot of, even for like how many layers, how we place this space, it's a very challenging problem. And we have all this theoretical proof. If you want more details, please like refer to our papers or take a look at our papers. We encourage you to do that. And the last phase is like after the peak load times, if you remember, I have showed the figures, the load also like got decreased at some time point after the peak time. And this time, the Oneiros also need to detect this time and also stop the parameter remapping. As I have mentioned, even like a perfect pipeline, but every pipeline comes with overhead, even like 10% of pipeline, there is overhead. So we don't want to enable like those parameter swapping, this parameter remapping when it's not necessary. After I have talked about the details of these remapping controllers, I also want to talk a little bit of some of my other work, because this also goes into details about the hardware level. I have another work which published at the ACM Taco Journal about the performance simplifications of pipeline data transfer in CPU GPU heterogeneous systems, which is part of the technical support for Oneiros. We have a detailed performance character studies of the CPU GPU data transfers. As an example here, here's the figure showing like how this CPU-GPU data transfer in a typical systems. So first step, we load the data from the CPU DRAM to GPU DRAM. And after GPU DRAM got the data, we could load this to the GPU SM, which is like the computational cores for GPUs. And inside each GPU, there is a shared memory or L1 cache belongs to each SM unit, and there are also computational threads for these computations. And for the computational data transfer techniques, we first studied unified virtual memory, which is about on-demand data transfer and per page granularity. So mostly it's about changing the programming model and to simplify the entire process. So previously, we need to do CUDA malloc to malloc a large chunk of data and copy the entire chunk of data from CPU memory to GPU memory, and after computation, it will store the data back. But with unified virtual memory, the drivers will handle this CPU GPU data transfer with just one like CUDA malloc managed, and it will only when the GPU SM unit in the data will copy this at a per page granularity to automate the entire process. Well, like the programmer do not need to control the process. There are also pinned memory. Like we also could pin the memory of the CPU DRAM side to make this part of the memory, like to part of them not swapped out by the OS paging like policies. This is the support for our like pipeline, the CPU computation and GPU, so CPU GPU time transfer data computation. We have to use the pinned memory. And there is also a further step of the asynchronous mem copy, which about the right side to pipeline the GPU DRAM to share memory copy with the SM thread computation, which about like also pipelining the right side of the computation. We have a detailed performance study of all these different computational like data transfer techniques, and we also make a benchmark suite to implement all these like data transfer techniques and to open source it and for these performance studies. And we have studied on 4 different machines with different GPU and CPU setups of different technologies, CPU GPU transfer technologies, and there are different combinations. The baseline is using the standard CUDA APIs, and we studied using asynchronous mem copy, unified virtual memory plus async copy, pinned memory plus asynchronous copy of all these different combinations. And we have figured out like different memory transfer techniques could affect the performance significantly. And we have detailed studies like to even like performance counter analysis to show like why the details, why this performance difference could come, and also give hints for programmers like how to use these cases, how to use these data transfer techniques. And we can see that if you didn't use this data transfer technique like correctly, it will could result in like more than 4x performance difference. And there's no data transfer mechanism that optimal across all workloads. And we have detailed study of this. If you are interested, please feel free to read more details of the other paper. Okay, let's go back to Oneiros. So for Oneiros, as we have mentioned, Oneiros is kind of like a supporting engine for existing LLM inference serving systems. So we have integrated into the LLM inference serving framework, which is vLLM. So currently, like when we develop this, we integrate into vLLM version like 0.7.3. But as we all know, like vLLM, they are moving very fast. They are like developing this all very fast. For their latest versions, they also have great support for multi-tenant systems. Or they also have great support for like KV cache. I believe they also have KV cache swapping enabled like in very recent versions. So which also confirm like we are in a good direction. And we have evaluated compare also against Pi, which is about the KV cache-based swapping methodologies, and evaluated within like dataset Alpaca and SharpGPT datasets. And we evaluated model like arrival patterns using the Azure LLM inference coding traces, which is about the figure I have shown before, which has a very large variance. And we have evaluated on the G200 machines, and we have evaluated different model combinations, which contains both OPT model and Llama model. And for the evaluation metrics, we evaluate the time to first token latency, which are about how fast your response of your system, what the exact latency will serve the first latency, will generate the first token. And time between token latency is another important metric for LLM inference serving systems, which is about the smoothness of your entire serving process. And we also care about throughput, which is about tokens per second, which is about the capacity your system can support. So first set of results, we compare between Oneiros and vLLM and Pi. So we have a lot of such figures in our paper. I don't have the time to go through everything, but I would like to go through how we understand these figures. So the x-axis means the request rate, and y-axis shows the latency, which is about lower is better for those serving latencies. And this figure shows the TL or P99 time between token latency, and this slide shows the throughput. Throughput is higher the better. As we can see here, so when is the KV cache running out of KV, we can see that for the vanilla vLLM systems, as you can see, at some time point, the server latency increased significantly, which means that you have to do the recomputation of the request if you are running out of KV cache. You have to, for this request, you don't have enough KV cache to allocate for this request. You have to do this computation. That's why it impacts the latency significantly. But with either Oneiros or with Pi, we could do this. We could use the CPU memory extension for GPU memory. That way, we avoid the heavy recomputation, which could make the latency in a stable manner. And because of Oneiros avoids bidirectional data transfer, we only use unidirectional data transfer, which helps reduce synchronization overhead. That's why we could help reduce the latency compared with Pi. And there are also results showing for different combinations of data sets in our papers. And we can also show that Oneiros constantly have better performance than vLLM. This is about latency, shows lower latency, and higher throughput than the vLLM for all these model combinations. Also, we have some case studies about the Oneiros design choices. Because for the first key challenge question is about when to start remapping or when to stop remapping. We compare the case of dynamic reversion and no reversion, which the no reversion means that as long as we enabled Oneiros, we do not stop it anymore. Even we are not about the peak load, the load also drops. We do not disable Oneiros. The parameter remapping is continuous doing this. We are continuous doing this overlapping computation and CPU-GPU data transfer, which is not necessary. So our system has to support that. When we know that we are not at the peak load, we have enough KV cache, we have enough buffered KV buffers, storage buffers. We do not need to. We can disable Oneiros, bring everything back to GPU memory and just disable this. We're just using the vanilla vLLM. That's sufficient. And how to understand this figure? This is mostly like a CDF plot. So the y-axis shows the percentage of all the requests. We can show, and the y-axis shows their latency. We can show that with dynamic reversion, at each percentage, for each request, we could achieve a lower latency compared with no reversion. This is very important when the load didn't reach the peak load. As I show here, the RPS, request per rate, is only 1. Especially this is effective for those non-peak hours. It would further help reduce the latency of the entire system. Another decision is how many layers to remap. One choice is we kept the remap, the number of layers. We don't want the CPU-GPU data transfer becomes the new performance bottleneck, which is called capped solution in our case. However, Oneiros also support the case of non-capped scenario, which is kind of to remap layers. Or excuse me, to remap layers as many as you want. As long as we run out of KV cache without parameter remapping. This is called non-map solution, which is kind of effective when the load is low, But when you consider the median part, it definitely increased the latency at the median point. And when the request coming even higher, the not that efficient because at some certain point, about some certain point, the CPU GPU data transfer is highly becomes really the new bottleneck of the entire system. Your system will not work like as effective as before. So our suggestion is to really need to this profiling guided this non-cap solution to set the maximum number of layers to remap would give you a more stable solution. But if you are pretty confident for some special cases, your coming request rate did not really reach it that high, you didn't have the RPS, the request per request reach it to 10, you probably could enable the non-cap, but you need to be very careful about this when you're deploying Oneiros. Okay, we also have more results, but due to time limitations, I don't want to present all of the results, but we definitely encourage you to read our paper and to go through all the evaluation results and all our design techniques. But to summarize my talk, so we are kind of make the observation that emerging hardware platforms provide increasingly higher CPU, GPU bandwidth. So it is possible for these KV cache or parameter remapping solutions to use the CPU memory as the existing as the extension for GPU memory. And because the existing solution did not use this, which is didn't fully utilize our CPU, GPU bandwidth. And KV cache swapping also incurs significant overhead due to the bidirectional data transfer. But instead, we use single directional or unidirectional data transfer by using parameter mapping, where our parameters they never change during the execution runtime, and we could dynamically rerun parameter to actually resize the KV cache. And also we develop a mechanism to decide when to remap, which model to remap, and how many layers, which layers to target. And I think that concludes my talk. And last thing I want to mention is that we have already open sourced the code of Oneiros and also the other previous performance studies. We also open source all these benchmark rate. So if you have any questions, so please feel free to reach to me, and also please feel free to try our codes. I'm happy to take more questions.
Thank you very much, sir, for accepting our request and delivering such an insightful talk. Are there more questions from the audience?
Yeah, so there are
Hi,
two questions.
one question. So, interesting talk, Ruihao. Wanted to ask, do you have any results on using any of the sparse models like the mixture of experts model with Oneiros?
Yeah, that's a very interesting question. Actually, we don't have the results, but yeah, we believe there might be opportunities and it's worth trying. Yes, but we don't have any results for now.
So, what do you think if you have sparse models, will it be even more beneficial as compared to the dense models like OPT?
Yeah, that's also a very great question. So I think that another challenge for those MOE or those sparse models is decide which expert is really you are utilizing which expert. I think they are, based on my opinion, it might go into another direction of this approach. There are also some prediction-based work to decide how to do the prefetch of this expert, because you see for those MOE-based models, the size of each expert may not be that huge. But really the challenge is to figure out which will be the next expert. I think maybe you have to go to another direction. Oneiros definitely we are really out of memory. You could use Oneiros, but I believe the other methodologies may be more effective.
Sir, as a follow-up to that, to this question, I have a small clarification. So in the mixture of expert thing that we have discussed right now, there could be heterogeneous experts, right, with different number of layers. Now, does Oneiros can assign say that if it is expert 1, hide X number of layers, expert 2, Y number of layers, something like that?
Yes, right now the Oneiros, if you go to more details of our paper, we have exactly a mathematical model to decide how many layers to map and which exactly layers to target. Right now, we are doing a very simplified linear model. We assume everything is the same, but it could expand to a pure intelligent linear program problem. It's just more complex, but I believe it's able to solve. It's just an integer linear program model. It wouldn't be a very big challenge for these heterogeneous things.
Okay, understood. Thank you, sir. So I think, sir, you have addressed almost all the queries. And thank you once again for accepting our request and delivering such an insightful talk. Thank you all audience for attending, and have a great evening.
Thank you so much.
Thank you, sir.